All right, let's just jump right in. Welcome to today's Explainer, where we are going to bust a pretty massive myth in the world of artificial intelligence right now. You've probably heard that if you want to give an AI robust, reliable memory, you absolutely have to build this massively complex, hyper-modern tech stack, right? You need dedicated vector databases, heavy message queues, just the whole 9 yards. But what if I told you that you could do it all and actually do it beautifully with good old PostgreSQL? Let's get into it.
I mean, think about it. Have you ever wondered why these genius-level AI agents basically have the memory of a goldfish? It is such a visceral pain point for developers today. Modern large language models are brilliantly smart out of the box for sure, but they suffer from this severe foundational amnesia. Literally, the second an inference call ends, they completely forget everything that just happened.
So here's our roadmap to demystifying all of this today. We're going to start with the AI amnesia problem, move to the taxonomy of memory, and then explore flat and filtered memories. After that, we'll dive into graph and temporal memories, then multi-agent swarm coordination, and finally, moving agents to production. From simple flat tables all the way to complex multi-agent swarms, we have got some fascinating ground to cover.
All right, part 1, the AI amnesia problem, or what I like to call the stateless trap. Here's the core issue. Because LLMs are entirely stateless, every single API ping is a completely independent event. The AI wakes up, gives you an answer, and immediately goes back to sleep. And this creates 3 critical failures. First up is the continuity gap, meaning there's zero user context carrying over between your sessions. Second is knowledge decay. If the AI makes a mistake, it literally cannot learn from it to do better next time. And third, the scalability wall. You might be sitting there thinking, hey, I'll just dump all of our chat history right into the prompt. But you are going to hit a wall incredibly fast where token costs just skyrocket and the output quality degrades into a completely noisy mess.
Let's move to part 2, the taxonomy of memory, moving way beyond just basic vector search.
To really fix this amnesia, we need to completely shift our mindset about how memory actually functions. Think of this as the journey from a goldfish to an elephant. On the y-axis here, we've got temporal scope, which is basically how long a memory lasts, all the way from transient working memory up to permanent archival memory. On the x-axis, we have structural complexity, moving from simple flat lists to incredibly rich temporal graphs and strict access control policies. And the reality is, different AI agents need totally different combinations on this matrix to actually function properly.
Which brings us to section 3, flat and filtered memories. We're talking workspaces, tasks, and enterprises. Let's look at our first archetype, developer workspace memory. Picture a coding assistant that needs to understand an entire massive codebase. This pattern uses a really clever hybrid approach. It uses cosine distance for semantic search, so it conceptually understands what the code does. But it also uses trigram similarity. Why? Well, because developers make typos. If you accidentally search for RECAL instead of recall similar, the symbolic trigram similarity catches it. It's a brilliant way to bridge the gap between raw code symbols and actual semantic meaning.
And this is where we get to bust a major myth. You do not always need a dedicated vector database for this. Seriously. Using Postgres with a simple PG_TRGM and HNSW SQL query, you can filter by project ID, filter by Git branch, and rank by vector similarity, all in one single native operation. For small to medium codebases, this flawlessly marries metadata filtering and vector ranking without the headache of spinning up and managing an entirely separate database service.
Okay, our next flat pattern is autonomous task memory. And this is where things get truly autonomous. This pattern gives agents what we call episodic trajectory recall. Essentially, before the AI even attempts a new multi-step goal, it searches its memory for similar past tasks. It creates an experience-based planning system. This means the agent finally stops repeating its past mistakes and actually adapts proven strategies for new goals.
But you've got to be careful. And the crucial point here is this number, 0.7. So what is that? It's your success score threshold. Think about it. If you just pull up the most similar past tasks, the AI might retrieve a past trajectory that completely failed. By enforcing a strict SQL filter where the success score must be greater than or equal to 0.7, you create the ultimate quality gate. Because without this metric, your AI is literally going to learn from its own failures, and nobody wants that.
The third flat pattern is enterprise knowledge memory. This one's tailored for corporate environments where access control is absolutely everything. It uses something called reciprocal rank fusion to perfectly blend exact keyword precision with broad semantic meaning. But here is the really important part. In regulated industries, you can't just casually hide confidential documents in the UI and call it a day. You have to filter documents securely at the database retrieval level based on the user's role. And guess what? SQL handles this natively and securely.
Moving right along to Section 4, Graph and Temporal Memories. Let's talk about tutors and companions. Let's dive into adaptive tutor memory. This is such a brilliant archetype if you're building educational AI. It represents skills as a directed graph, kind of like a massive skill tree in a video game, but it adds temporal memory. Think of those spaced repetition flashcards. The AI doesn't just need to know what you learned today, it needs to mathematically model exactly when you are likely to forget it, so it knows precisely when to schedule a review session.
And here's the coolest part for the developers out there. Instead of the AI agent having to download massive datasets just to crunch those numbers manually, you can literally drop the Ebbinghaus forgetting curve math directly into your SQL query. The Postgres server does all the heavy lifting, computes the decayed scores instantly, and just hands the AI exactly what the student needs to review. It is so incredibly efficient.
Next up is the relational companion memory. Now, this is the most complex schema we're going to look at today. It models the most human-like autobiographical memory we've seen so far in AI. It is simultaneously juggling long-term persistent facts, permanent episode summaries, and short-term feelings all at the exact same time. So companion memory basically operates across three distinct domains. First, you have graph memory for persistent facts, things like Alice lives in Brooklyn. Second, episodic memory, which acts as an archival summary of past conversations. But the third one, ephemeral memory, that's the secret sauce. It uses a time to live or TTL expiration for things like transient moods. Like if you tell the AI you're feeling super stressed today, it shouldn't hold on to that fact forever. Using a database expiration mechanism keeps the long-term memory totally clean from outdated, short-lived feelings.
All right, Part 5, Multi-Agent Swarm Coordination.
So what happens when you have multiple specialized AI agents sharing a workflow and you need them to not step on each other's toes? You might assume, okay, now I definitely need a massive message queue like Kafka. But you don't. You can just use Postgres's ridiculously elegant for-update skip-locked mechanism. Here is how it flows. An agent looks at the database blackboard, and Postgres places a row-level lock on the first pending task. If a second agent shows up just a millisecond later, it dynamically skips that locked row and just grabs the next available one. The first agent updates its row to in progress, and boom, zero race conditions. It is a perfectly coordinated local swarm using nothing but a built-in database mechanism.
Finally, Section 6, Moving Agents to Production.
Now, the architectures we just explored are amazing for retrieval, but they are primarily single-shot read-only pipelines. To build a true production-grade agent, you need complex workflows. It needs the ability to actively call tools, run in continuous feedback loops, and use conditional edges to make logic decisions on the fly.
To take these patterns out of the lab and into a scalable enterprise environment, there are a few absolute must-haves. First and foremost, you need bidirectional read and write memory. The AI cannot just be reading from the database, it has to actively write new memories back to it. You're also going to need a checkpointer to save state during multi-turn chats, sub-agent fanouts for complex swarm tasks, active context pruning to keep your token costs from exploding, and robust observability to monitor the actual quality of the outputs.
Which leads me to a final, pretty provocative architectural question that you really need to ask yourself as a developer. Is your agent an observer, or is it a participant? If your AI only ever retrieves data from a database, it's really just a passive observer. For production AI to truly act as a genius-level participant in your workflows, it has to actively forge new memories, learn from its own experiences, and constantly write those fresh insights back to its PostgreSQL core. The patterns are all right there, and they're incredibly powerful. Now it's up to you to actually go build it. Thank you so much for joining this explainer, and keep learning.